Hello folks, I don't think I'm ever going to finish this video. A recreation of Walter Lewin's elastic collisions experiment, bouncing unequal masses into one another, something like that. But there's a lot of information here that you can still enjoy, get some use out of. It's not perfect, I accept that. I should have made sure that the bits in the trolleys didn't sometimes roll about a little bit. Go. But it doesn't seem to have made much difference to the experiment though, because you can see that from the graphs where I show you the theoretical curve for these 31 different experiments, 4 kilograms into 4 kilograms, descending 100 grams at a time down to 1 kilogram into 4 kilograms. The graph shows the ideal, the theoretical perfect response we should have had. Below that you can see the actual result we got, and there's one or two kinks in the curve, where there are obviously some imperfections in my system, but it's pretty close to the theoretical result. Then there is a straight line result that would have been Gary's theoretical prediction. Anyway, I'm just going to piece together some of the information, let you enjoy it for what it is. See 31 experiments, one after another. Really, this should be taken by somebody else in a better position than me to do the experiment again better than me. You know what I mean? Instead of just criticising it, as Gary's bound to do, this should really be their cue for them, Gary or one of his fans, or anybody really, in a better position than me to do these kind of experiments, film them well, document them well, and not lose motivation like I tend to. I get bored easily, I've got to be honest. It soon gets boring to me. Anyway, I've done the work as best I can, and I'm sorry it's not perfect, but I did my best. Anyway, enjoy it for what it is. Thank you. Bye. Just to clarify what you're going to see in this video, you're going to see 31 elastic collisions where I roll this homemade low friction wheeled cart made with old hard drive discs, very low friction bearings. 31 experiments that are all very similar, and there are 3 stages to each experiment. Okay, first of all, I launch this by compressing this spring against a solid surface, which launches it with the same force each time, so that the other end hits the other heavier cart, which is always set at 4 kilograms. This is the other one. This is an identical cart made with the same wheels, but it's weighed down to 4 kilograms. You can see there. That's a British fuse that you put in a plug in Britain, because we have a higher voltage in Britain. It's not your namby-pamby 120 volts. We use 7,000 volts in Britain. Yeah, we do, yeah. Just jesting. 4 kilograms anyway in total weight. So that will then roll off at a slower speed than this one hit it, except when this is weighed down to 4 kilograms too. So initially, that cart and this one are the same weight. When there's nothing in this, it weighs 1 kilogram. I've written there 1 kilogram. So I start off with it 4 kilograms hitting into 4 kilograms elastically. Properly elastically, with aircraft grade springs, really good quality springs, quite expensive, but reliable. None of Gary's homemade ones where he winds them up with copper wire. When this is 4 kilograms and the other one is 4 kilograms, there is, as near as damn it, an exact exchange, a bit like Newton's cradle. So when they're both 4 kilograms, it's a bit like Newton's cradle when they bounce off one another exactly. The energy from one gets passed entirely to the other one. But the important point to take away is that in each case there's going to be 3 stages to the experiment. This rolling forward, you'll see the frame count, which automatically happens. Stage 2, the spring bashes into this and pushes this forward at a certain speed. And again, you can observe the frame count. So basically, you're going to see 31 instances of me rolling this cart with the same force, but at different weights, into this 4 kilogram weighted one. See a piece of metal sticking out there? That piece of metal coloured blue and the other one is coloured red. That rides over a tape measure, so you can read off how many frames it took to travel 200 millimeters. 200 millimeters is the set distance I've been measuring over. 20 centimeters, about 8 inches. So there are 3 stages. The incoming speed of this, the outgoing speed of this 4 kilogram one, and the reflective speed of this one going backwards again. And those 3 speeds depend on the masses. When they're both 4 kilograms, this comes in with one speed, This goes out with almost the same speed, 97% the same speed. Should be 100 if there were no losses in the system, but no system is perfect, therefore we have some losses. In that case, when this is 4 kilograms and that's 4 kilograms, this isn't going to bounce back at all. It's going to stay still because it's passed all its energy onto the other 4 kilogram one. Bit like you see with snooker balls. One snooker ball hits another one directly, it stops dead and the other one takes up at its speed. It's that simple, but 31 instances of it, there's going to be a lot of information popping up on the screen quite fast, so you might get a bit lost if someone doesn't explain to you first what you're about to see, and that's why I'm here. Okay, Gary, so do you agree or disagree with the following experiment? Or my version with heavier carts, 4 kilograms each. And what do you know, it stopped dead on. Stopped dead on. And now that's stopped dead on. So it was an elastic collision. It was doing exactly what I think that you would have predicted it would do. I think you would have agreed with it. I don't think you have any argument with that particular experiment, do you? Well, what if I reduce the mass of the incoming cart from 4 kilograms to 3.9 kilograms, say? What do you think will happen then? Pretty much the same thing? Here we go. Yeah, I don't think you would be surprised that it does pretty much the same thing. It just tries to bounce back a little tiny bit, but it's hard to measure. Here we go. Okay, so let's make it a little bit smaller again. Let's try 3.8 kilograms. 3.7. 3, 2, 1. 3.6. 3.5. 3, 2, 1. You've probably noticed by now that the lighter cart has started to rebound off the heavier one, but only a little bit. If you can see the pink arrows, those indicate the distance that the light cart rebounds back in the same space of time that the 4 kilogram cart has moved 200 millimeters. But the point I'm trying to get across is that there's nothing physically wrong with the experiment, is there? You might want to argue that I've not yet showed you me weighing them. I can show you that later. But there's nothing wrong with the experiment, is there? And obviously in that first example, the 4 kilograms should have transferred 100% of its speed to the second 4 kilograms. But it only transferred 97% of it. But I'm sure even you can live with a 3% error. Walter Lewin accepted a 2.5% error, so I'm sure even you can accept a 3% error from me, not Walter Lewin. Well, supposing we carry on reducing the mass, let's jump to, say, 3 kilograms. Still only rebounding a tiny bit more, so let's try 2.5 kilograms. Go. The changes are becoming more and more obvious, aren't they? So let's go to 2 kilograms now. Sure. Well, you can now see that we've transitioned to the exact same experiment that Walter Lewin did on an air track. We're getting 65%, should have been 66.6% by rights, but as you saw at the start, we had a slight error because of imperfections in the experiment. But we have substantially reproduced, effectively, Walter Lewin's experiment. So we've got 2 carts. This one I can vary between 1 kilogram and 4 kilograms. And this one I'm leaving fixed at 4 kilograms. So just let me verify those weights for you. So it's zeroed with that on. So that's as near as damn it, 4 kilograms. Okay, I'll do the other one.
Yeah, 4,001 grams. Then what I'm going to do is start taking off these pieces of metal. I've weighed those to 100 grams each. I'll show you that. I've made it so these all weigh 100 grams each. Oh, okay, 102, 101, 99. Okay, averaging 100. Okay, well, I'll check them all now. 100. So the experiment I'm recreating is Walter Lewin's elastic collisions between unequal masses. So the way it's supposed to go is, if we have a mass here of 4 kilograms and we hit it with a mass of 2 kilograms, exactly half that mass, this is still 4 kilograms, isn't it? But if we hit it with 2 kilograms, that's supposed to take up 2/3 of that velocity, and that bounces back with 1/3 of its velocity. But before I do that, I'm going to work backwards towards that point. I'm going to first of all do 1-to-1 ratio, because that's easy to check whether we've got it right or not, because we've verified that that's 4 kilograms, and we've verified that that's 4 kilograms, and the theory is, everybody knows I think, that when this hits that in an elastic collision, this is supposed to stop dead, and that's supposed to carry on and take up its motion. So let's see if that actually happens. Then what I will do is I will start to reduce the weight of these 100 grams until we get down to 2-to-1 ratio or 4-to-1 ratio. Okay, so let's make a start. Now the way I'm doing it is I'm compressing this spring at the back. I'm compressing that against a rock solid, hard, very, very, very heavy loudspeaker that isn't going to move. It's like a brick wall in effect. So it's going to push off that the same every single time, because I'm going to compress it the maximum compression each time. And you can tell it is because when this red marker is level with that pink line, okay, so I just have to let go. I've marked the start line there. And what do you know, it stopped dead on. Stopped dead on. And now that's stopped dead on. I'll do that just once more, just because it's quite fun to watch. And let go. And once more, it stopped dead on. Now I'm going to remove one of these, and that'll make it 3.9 kilograms next. That's as close as we're going to get it, isn't it? Sorry, I'm suffering with a bad chest. 3.9, here we go. Take another one off, 3.8. Here we go. Take another one off then, 3.7. 3, 2, 1. Take another one off, 3.6. Ready, steady, go. It's like it tries to push back, but it can't quite. So take another one of these off then. So now we're on 3.5 kilograms, okay? 3, 2, 1. .4 kilograms. I'll just verify that with the scales. 3.399, is that it? Yeah. 3.4 kilograms, 1, 2, 3. So take another one off. 3.3 kilograms, go. See, it's gradually starting to roll back, isn't it? .2 kilograms to 4 kilograms. Go. 3.1 kilograms to 4 kilograms. Go. Get another one off. So now it's 3 kilograms to 4 kilograms. Ready to go. .9 kilograms to 4 kilograms. 2.9. It's now rolling back more than it did before. Take another one off. 2.8 kilograms. 81 go. Let's push him back. .7. .6. And off it goes. .5. 3, 2, 1, go. Let's verify that we really were at 2.5 here. There you can see it. 2.4 kilograms, 2.4 go. Take one off then. 2.3 kilograms now. 3, 2, 1. .2 kilograms next. I'll take one out. 2.2, go. .1, 3, 2, 1, go. So we're now on 2 kilograms to 4 kilograms. 2 to 1 ratio. I'll repeat that, okay. That's an important one. 2 kilograms, 2 to 1 ratio, go number 2.
Go number 2.
1.9. .8 kilograms. 1.8, go. .7, go. .6. Because there's less weight in the cart now, it's more apt to slip. 1.6, go. See what I mean? Because there's not enough weight in the cart to hold the back end down. Some weight in the back rather than the front. 1.6. .5 to 4 kilograms. 1.5, go.
I did try to make sure that the weights didn't slip within the cart, but because the carts are getting so light now, it's getting harder and harder to stop the things slipping about inside. If I did this again, I would put some cloth inside or use some blue tack to hold things in place. But hindsight is 2020, isn't it? So we can see that the reflection speed increases exponentially as we decrease mass.
So that's 1.4. 1.4. The camera crashed. One point three. 1.2. 1.2. One point one. 1.1, okay. 1.97. 1 kilogram, okay. One kilogram.